Good afternoon, everyone, and welcome to the session. My name is Dr. Simkar, and I'm a faculty member in the Space Studies Department of the American Public University System and the moderator of the session. If you have any questions, please type them in the chat box and we will address them during the question and answer session at the end of the presentation. It is an honor to introduce the presenter, Dr. Kathleen Ahrens. Dr. Ahrens is a postdoctoral researcher at the NASA GSFC. Her research focuses on remote sensing of icy surfaces and volatile interaction, particularly at lunar poles and cryovolcanism. She models thermal phases of ices and studies planetary volcanism on Mars, Ceres, Titan, and Pluto. In 2018, Dr. Ahrens also received the 10 Outstanding Young Americans Award for Science Communication. Now, I invite Dr. Kathleen Ahrens to give her presentation on the topic, a RAD Adaptive Support Framework for Lunar Exploration.
All right, thank you for that introduction. Good morning, afternoon, evening, all around. So super excited to be chatting about our team's latest funded project. So this one is it's a fairly new pilot program coming out of the NASA Office of Technology and Space Policy. So this is going to be sort of a preliminary outline as to what our team is going to be up to. It's going to be some exciting stuff. Happy to answer questions about lunar science in general, how we're getting ready for Artemis. But essentially what it comes down to is there's just so many decisions that need to be made from the scientist point of view, from the engineers and the technologists to the policymakers. And we all have to join in together to make all sorts of decisions as well. So I'd like to also thank Lalachi, Lynch, and Petro for being on this team as well. So we're going to do a little bit of background as to what I mean by the different kinds of decisions that we're going to be making on the moon. What is RAD, how we're using RAD on Earth, and how we can apply this to the moon in some of our team's future work. So looking at current lunar studies, our past, present, and future, we have a lot of lessons learned from the Apollo missions, and that's exciting. We've definitely had some whoopsies during the Apollo missions as well. What does that look like going forward? We're going to a part of the moon that we have not been to before. So that's exciting. But that also means there's a lot of hazards involved. There's a lot about the lunar environment we still don't really know as well. And then sample return. So part of my job is to looking at volatiles on the moon. So a lot of that ice, how can we sample it and return it to Earth safely? Can we use it as like a resource management as well? And then how do we make sure that what we collect and how we sample it is safe as well? So there's got to be some sort of hazard management and preservation as well, not just preservation for the natural environment, but preservation of other sites as well. So whether we want to keep these as cultural sensitive sites or also historic sites as well. So the Apollo artifacts that we still have all over the moon, how do we preserve those in a sense? And then also advancing technology as well. So as we like to say, tech showcases. This is how we advance our technology. We want to be able to make them space-worthy. We need to test them at the moon. So how do we make sure we go about this in a very ethical way, a very safe way, but also progressing toward what we need to do? And certainly when there is private sectors on the rise. So that communication between federal agencies, international collaborations, and private sectors. So from the Science Policy Office of NASA, there was a report not too long ago called the Artemis Ethics and Society Report. It's a great read. I highly recommend taking a look at that. It is open to the public. It goes about these three aspects here: the theoretical, the decision process, and the forecasting. And you might be wondering, like, what's the actual difference in all of these? Well, the theoretical and decision process goes in two different ways. The theoretical is the conceptual part. What are the defining, essentially we're laying out the definitions of what we're working with. So that would be the theoretical part. The decision process would certainly be making sure we're going forward with being ethical, sharing ideas, sharing cultural values, making sure that we're being aware of historic interests, but also cultural interests, making sure we're being reflective of each other's decision. Now, forecasting is kind of bringing all of these concepts and definitions and perspectives to go forward with that. So the two major things here is the flexibility for change, and then who makes the decisions, who does the communication come from, and who does it affect? What kind of ripple effect would we bring about with this? But the common theme between who makes the decisions and the communication part and the flexibility all comes down to adapting. Any decision that is made for lunar science, whether it's an instrument to full grand scale sustainability, lunar presence on the moon, isn't that exciting? Any little detail, it needs to be adaptable because there's a lot of unknowns about the moon, and it's not a one size fits all solution either. So what is RAD? RAD is a lovely acronym for Resist, Accept, Direct, and I'm going to take notes here from the National Park Service. They have a lovely definition of the Resist, Accept, Direct initiative involving a boat. Which is why I have this boat here. So pretend, if you will, visualize with me, you're on a boat. So you go out to sea, and maybe a storm is approaching. What do? And you're far away from shore, but what do? So do you resist? You just keep going and hope for the best, and maybe you think, oh, you know what, I know this area, the storm's not going to last that long, it's only going to be 5 minutes, it's not that bad, we're just going to keep going? Do you resist any sort of change? You just keep going to your destination? Do you accept the change autonomously? Maybe the storm is making the waves kind of make you go to back to port. Maybe it's actually having you change direction ever so slightly. Maybe you're like, you know what? This storm is like super bad over here. It's not so bad over here. We're just going to do a little bit of a natural progression over here out of safety. Or direct change. You're just like, nope, you know what? We're just going to head back and deal with it later. We're just going to just, nope, this storm out of here. So it's all in the decision of, do you resist change? Do you accept it in a more natural flow? Or do you directly shape that decision? As well. And by all means, there will be times when some of these definitions may be like, oh, well, it could be this, but it's kind of skirting into this. Well, what about this? That's the point. That's the point here, is that a lot of these decisions are what if, then this kind of deals. And we use RAD. We use RAD for Earth studies. So a lot of wildlife refuge is across the globe uses RAD, and using it as a form of decision making. It's specifically adaptive too. So just some examples here. So the Chaffee National Wildlife Refuge decided resistance to change marsh migration. So resisting that, deemed infeasible, both economically, it would have really been a huge huge issue, economically, but also environmental as well. Just it would have made things worse before it got better. And we're like, you know what? Let's just resist the change. It just let it go. Restoration success. Chincoteague, this one accepted the changes involving the natural environment, and then Blackwater did direct changing. So they eradicated and very much controlled by introducing different flora and fauna into their marshlands to then actively shape their environment. Now, what I'm saying here is based on Earth is not just natural management. I mean, most of this is natural and management, but for the moon, we have to do both between natural management of the moon and also human management, aerobatic management of the moon as well. So as we are just, sending people and robots back to the moon, even just moving around the moon, kicking up dust, using instruments on the surface, you're actively doing something to the surface. And whether it's in some small part and then you clean up after yourself, great. If you leave the equipment there due to science, that's a decision. That's okay, but it's still a management decision that needs to be accounted for. So what happens here with using RAD? And it all comes down to these four separate themes. It's what's the science being delivered? So if you are resisting, accepting, or directing that change within your environment, you're going to get different science outcomes involved. So adaptation, either the environment itself is allowing you to adapt your decision, or vice versa. Your decision is adapting to maybe a different decision upstream, and it's now trickling down. So again, all that adaptation, especially for an unknown environment. So like the lunar surface, a lot of the resources we know about the moon due to remote sensing observations, we don't really know at what level a lot of these resources are on the surface. So then that goes into helping managers protect a lot of these natural resources, and then collaborating and outreach. So having not only private sectors, but also the public sector as well, helping make some of these decisions. The moon is a shared space, it's a shared environment. And so whether we have public support to learn about the science of the moon, that's great. But then when it comes to mining operations and how do you mine versus preserve, that's where it's going to have all these different kinds of communications involved. So another thing too is RAD frameworks have been used a lot with fish wildlife services, land management, tribal commonwealths as well, and commissions, Association of Fish and Wildlife Agencies. So RAD has been used quite a bit for flora and fauna. So there's no flora and fauna on the moon. What in the world are we going to do about that? But it is all going to come down to managing our time, managing our activities, and managing our resources at the moon. So what does this potentially look like? We don't just go to the moon willy-nilly. We know that we're going to go to the South Pole of the moon for Artemis. Why? We have defined our objectives and goals of why the South Pole at the moon. What kind of resources can we get there? We know that there's ice on the moon. So there's now implication for the architecture. What kind of instruments do we want to bring to the South Pole of the moon? What kind of sampling do we want to do at the South Pole of the moon? And then how do we execute it? So actually getting there, making sure we can manage our time efficiently, make sure we manage our equipment there efficiently. Obviously, the safety of the astronauts too. Astronauts during a very typical lunar surface operation is about 8 hours. Got to make those 8 hours count. So RAD essentially would help with this architecture need here. So what are the priorities? What is the management goals? What are the kind of different decision making going on, especially if something doesn't work out, which could happen. That's a possibility. So if something doesn't work out or something that was unknown to us that we are like, oh, we now learned a thing on the moon. That's exciting. That can affect our decisions. And again, we got to be adaptable. So this is just a very preliminary aspect of what our team is working on. We do have a few papers coming out hopefully soon, so stay tuned for that. But again, here's just some very broad brushstroke themes that we're looking into. So say if like again, you're resisting that trajectory, you're kind of maintaining status quo going on. So this can include preserving or even restoring historic landing sites, whether it's historical or heritage significance. So that could be Apollo, it could be surveyors, it could be Luna landings. Whether if we do accept making the change autonomously. So in this case, limiting the number of vehicles within a given space, within a given area. If you have way too many robotic and human aspects in an area, you're going to end up with interference. So how do we make sure we reduce interference there? We have dealt with interference accidentally from Apollo, so we already know like, oh, there's a lot to still learn about interference. And then direct, actively shaping that decision, that change. And so this would be further along. This would be using the lunar surface to build. We're actually taking the resources of the moon and using them directly. So this could be the water on the moon and we're using it for fuel. This could be using the regolith and making bricks and building structures on the moon that is actively shaping the environment. So with all of this in mind, by all means, the work that we're doing is still very preliminary. Like I said, we just got funded to do this and work on this. We're chatting with a lot of USGS folks that actively use the RAD framework across the globe. So learning about decision making, especially with uncertainties as well. And then we certainly want to continue communicating our work as well. So the CISA conference has been a fantastic platform for us to talk about this as well. But it's essentially getting everybody aware that there's so many decisions to be made when exploring the moon, going to the moon, and eventually having a sustainable presence at the moon as well. So adaptive decision making is key to getting to the moon, getting back to the moon, and developing on the moon, whether that's technology, it's economics, it's ethics, it's space law, it's space policy, all of these things are going to have very active decision making. And so all of this is going to have to be communicated in some aspect. So with that, I'm happy to answer questions. Thank you so much.
Thank you so much, Dr. Kathleen Ahrens, for your insightful presentation. And it was really very informative, and we learned a lot from your presentation. Um, it is really very important to make our management policies in such a way that they can handle the dynamic changes in the lunar surface activities, um, driven by both um, human interferences on the lunar surfaces, driven by increased human and robotic missions. We learned a lot from your presentation. Thank you. Any questions? Okay, thank you so much for your presentation, and we end this presentation. Thank you again.
Thank you.
Thanks, everyone, for joining us, and we wish you all the best.
Thank you. Bye bye.